Okay, so let's start. Let's start this Telecom seminar, which is hosted by the Technology Innovation Institute in Abu Dhabi. I'm Dr. Daniel da Costa. I'm currently a principal researcher at TII. And for today, I'm pleased to introduce Professor Honggang Zhang from Zhejiang University as the speaker of our seminar. For today, Professor Honggang Zhang will talk about a very emerging, in hot research topic, which is semantic communications and semantic coding. Then basically he will provide a very good overview on the existing semantics-aware communication techniques and talk about the underlying drawbacks of the current schemes. And he'll propose some mechanism for this semantic coding problem and putting forward a reinforcement learning semantic communication solution. And hopefully we can have a very insightful and informative seminar where the main insights related to how semantic are processed and represented in this semantics-aware communication and coding system. This can be pointed out and highlighted. So before I move into the talk, let me introduce Professor Honggang Zhang. So Professor Honggang Zhang received the PhD degree in electrical engineering from Kagoshima University in Japan in March 1999. And from October 1999 to March 2002, he was with the Telecommunications Advancement Organization of Japan as a TAO Research Fellow. From April 2002 to November 2002, he joined Toyota IT Center in Tokyo, Japan. From December 2002 to August 2004, he has been with the UWB Research Consortium and Communication Research Laboratory and National Institute of Information and Communication Technology of Japan. And from September 2004 to February 2008, he has been with CreateNet in Italy, where he led its wireless team for exploring cognitive radio and UWB technologies. And he participated in the European FP6 and FP7 projects. He was the main contributor for proposing DS-UWB in a IEEE 802.15 WPN-UWB standardization task group. Professor Honggang Zhang served as a chair of technical committee of cognitive radio. He was also the chair of many symposiums, IEEE symposiums, such as GlobalCon 2008, ICC 2013. He was the founding TPC co-chair of CronCount 2006. He was the general co-chair of IEEE GreenCon 2010. He is the co-editor of 2 books with the titles Cognitive Communication, Distributed Artificial Intelligence, Regulatory Policy and Economics Implementation. And the other book is called Green Communications, Theoretical Fundamentals, Algorithms and Applications. He is currently the Associate Editor-in-Chief of China Communications. Professor Honggang Zhang is also the currently the Chief Managing Editor of Intelligent Computing Journal and a science partner journal jointly established by American Association for Advancement of Science and Zhejiang Lab. He is a full professor of College of Information Science and Electronic Engineering in Zhejiang University, China. He was an international professor, ComLab's Excellence Center in Supélec in France, and he was an honorary visiting professor of University of York, UK. So Professor Honggang Zhang, thank you once again for accepting our invitation. And without further ado, the floor is yours.
Okay, great. Thank you, Professor Daniele and Benavides da Costa.
Yeah, Benavides da Costa, yes.
Yeah, okay. And of course, surely, thank you for your very detailed introduction on my CV. It's highly appreciated. And of course, I appreciate this very valuable opportunity to give our recent work on the semantic communication. So now I will share the slide to my dear friends here. So I share the slide here. Please wait a minute. Okay.
Yes, perfect.
Yeah. So as planned, from now on, I will give a seminar talk on the semantic code and the semantic communication. So first of all, I would like to give my big thanks to all the friends, all the colleagues here. And I appreciate their time, and I appreciate the interest, and I appreciate your efforts here to move forward together on the research of semantic code and semantic communication. So before going into detail of my presentation, of my talk, I would like to announce that this work is a joint work within my lab, together with my student, Qingyang Zhou and Bleu, and my colleagues, Longpen Li, my co-authors, Xianfu Chen, and my colleagues, Zhifen Zhao. So here is the, outline for this seminar. First of all, I will give some background information on modern communication, and then I move to the semantic code. Thirdly, I will move to the semantic communication. Finally, let's hold the discussion and summary. So first part, modern communication, a rethinking on modern communication. Yeah, I believe all of you are quite familiar with this slide, and so it's just a general picture on how complicated our modern communication is. So here you can see we have the space satellite communication, we have the UAV, we have the land terrestrial communication, and we have ocean, we have the underground communication, we have outside door, we have the indoor. So the whole picture of our modern communication is too surprising, complicated. So, and let us move to the next slide. As you know, and now we are in the era for thinking of 6G. And as far as we know, 6G will be started commercially from the 2030. And now we are at the very beginning for research, for studying the new era of 6G. And from this slide, you can see, of course, we have some kind of very excellent vision on how will 6G be. For example, latency will be 10 times shorter, spectrum efficiency should be 3 to 5 times, increased, and the experience data rate, peak data rate should be even 20 to 100 times higher, and the connectivity density will be 10 times compared with the 5G. And here you can see the roadmap for the future 6G development. But my question is, if we look at those something linear times, so if is that the real we want the direction from now on? Okay, so let us move to the next slide. So here we have some vision from European, 6G projector, XRX projector. And a very interesting scenario there. We can see some robot-to-robot communication, machine-to-machine, and even virtual reality, remote reality, something like that. So that's fantastic. Application scenario, application vision to be considered. And here, also within China, we have 6G ANA, and means 6G lines of network AI. So here, we also have a picture on the how will modern communication, how 6G will be developed from now on. And of course, you can see, you still feel it's very, very, complicated in terms of architecture and application scenario, right? So here, I believe, at least personally, it's time for give a rethinking on modern communication, to give a rethinking on how communication will be evolved, will be established, will be built up from now on. So here, let us have a review on how communication has been developed for the past 50 years. And here, in the last century, in 1949, and a very excellent paper published by Shannon and his colleagues Weaver, named the Mathematical Theory of Information. From that paper, we can see that now the communication is almost limited to the first layer, the lower layer, means the physical channel layer. And if we go outside the box, go outside the room, we will have the second, the upper layer, means the semantic layer. And on top of the semantic layer, we will have the effectiveness layer there. So until now, all of the, maybe it's too big mouth to speak that almost all of the research application have been focused on the first layer, means physical channel layer, and we have totally until now ignored the upper layer, means the semantic layer, and even effectiveness layer. So here, here I use this picture here. We are not Sisyphus. I mean that communication is not just transmitting bits. We should consider some, something like the real meaning of bits, real meaning of a symbol, real meaning of words, real meaning of a sentence. So from this perspective, for us, it's necessary to give a rethinking on the so-called semantic communication. I call it Turing capacity. So until now, we have been focusing on the Shannon physical layer channel capacity only. Now it's time to move further, one step further, to be outside the room, to be outside the box, to think of the so-called Turing capacity from the perspective of semantic communication. So it's time, it's the right time, I believe. So, okay. Okay, I am just read the message from the audience, from our, so here, let me give a thinking, just give a preliminary thought on how is semantic communication and how is semantic code working together. So you can see that from the left side, we have left part of this slide. Of course, we have the very general communication system. We have the source encode, we have channel encode, then we have modulator. You're quite familiar with that. Then we move to the channel. After channel, we have at the receiver side, we have the demodulator, channel decode, source decode. So that's the general communication system, right? And let us look at the middle part. Middle part, we can see the key point is how to preserve the semantic, right? And also for every message we want to transmit, the key point is how to get a high bit level accuracy and reduce the bit flow. So from those two sides, we have the semantic coding technique and we have the semantic communication technique here. So that's our general, view on how communication will be developed from now on, or how the general picture of future communication should be. So from now on, I will give some detail on the second part, semantic coding. Semantic coding here, here I put my the publication from my lab, from my colleagues, and if you have any interest, of course you are welcome to refer to these papers. And here, first of all, I will give introduction on explain on semantic coding, and as you can see these pictures, and from left side we have the transmitter, and on the right side we have the semantic receiver, right? And between them we have the wireless channel. So as I explained, we should be outside the traditional communication box. We should be outside the room, and on top of the physical layer, we should consider the so-called the semantic layer. And here we call it shared common knowledge. So on top of the physical communication channel layer, we have the so-called semantic channel. And for the semantic channel, we have common knowledge. So that's the key point here. So for a semantic coding system, from the source, we have the information input, and we have semantic encode. Then we move to this channel encoding, and then all the signal will be transmitted through the wireless channel, and then to the channel decoding and semantic decoding. That's a whole coding, semantic coding system. So here I want to present that. What's the key point here? What's the key idea here? The point of the key idea is semantics meaning. First of all, semantic means, of course, things. And the more important thing is semantic means relationship between the different bits, relationship between different symbols, relationship in between different words, relationship in between different sentences. So that's the key point here. My present opinion is that until now, all of us almost ignore the so-called relationship between the bits. And we just think the bits are just randomly distributed. We give them the equal distribution probability, and we then calculate the capacity, so-called Shannon capacity, right? But the key point here is that if we give some view, give some thinking on the relationship between bits, that will change the whole world. Okay, so that's the general system for semantic code, coding system. Here we use the transform, encode, and decode. I believe some of you are are familiar or at least know something about transform. So transform is recently very popular, very powerful, algorithm in the area of natural language processing, NLP area. So here I just first of all give you a very general picture on transform, on the semantic code based on transform. So from the left side, we have input information, and then we have the semantic coding, encoding encoder, right? Then we move to the physical communication channel, and then on the receiver side, we have the semantic decode. And here for semantic code and for semantic decode, we use the transform. So on transform, let us move this slide, second slide here. So for transform, as I explained, the transform is a very powerful algorithm in recent years with attention mechanism. So here we just a little bit detail on how transform works here. So we have, let us see the right picture. Of course, we have input, date, and then we move to the so-called head attention block module, and then we add and we give addition and normalization to this sentence words, and then we move to the next block, next module, feed forward. Then we give the calculation of addition and normalization again. Then we just after this step, we move to the output side. Output side, we just input the first block information to the masked multi-head attention module, then to the multi-head attention module again, then feed forward, then normalization, then soft mask. So that's how the attention mechanism-based transform works. So that's the key point here. And here, transform now, has been very, very powerful in processing the words, the sentence, and in the area of natural language processing. So the right side, on the right side of the picture is the very general ordinary transform, just as I explained. And so we use the transform as an encoder, a semantic encoder. Also, we use a transform of the semantic decoder on the receiver side. And so each semantic, transform-based semantic code, you can see that divided in several sub-layers and with multiple head attention, normalization, feed forward. Similarly, on the receiver side, we have the transform-based semantic decode, and the input information is passed through the multi-head attention, normalization, again, sub-layer of multiple head attention, forward, add, normalization, and soft marks. So that's how the general architecture of transform works. But here, on the right side, we have so-called universal transform. And first of all, let me just give a little bit detail on how universal transform it is. So comparing with the general transform, the right side is universal transform. You can see from the right side, we have, of course, a self-attention module. We have, of course, the normalization module. And so, of course, And on the receiver side, we again have the attention module, have the normalization module, again, multiple head attention and normalization. So the difference is for the general transform, we just have several layers. For example, encoder side, 2 layers, and on the decoder side, we have 3 sub-layers, right? But for the universal transform, we can see we have the feedback. For the encoder, we have the feedback. For the decoder, we have the feedback loop. So it means that we can control how many sub-layers we want to use. Also, we have the feedback from the output of the encoder, feedback to the input of semantic encoder. Similarly, on the semantic decoder, we have the same architecture. So that's very, very useful. That's very important for us. Now let's move next slide here. So as we know, voice channel is always varying. I mean, we do not have, stable voice channel as, always. So means that if our transmitter could be adaptive to the changing signal to noise ratio of voice channel, and according to the condition situation of voice channel, we can control the attention loop of transform according to the channel state information, according to the feedback from the receiver side. So that's the how our communication system works previously, right? So here we also want the semantic code scheme could be adaptive to the real channel condition as far as the transform of the transmitter side knows the channel state information, knows the SNR receive as SNR value. So the transmit based on the universal transform can change the loop. If the channel condition is good, the transform a semantic code just use 1 sub-layer. If the channel state transmit should use more loop, more sub-layer to increase the performance of the transmitter. So that's the key idea here. So that's why here we use the adaptive universal transform encode. Similarly, on the receiver side, we use the adaptive universal transform decode. Means that the receiver side and the transmitter side both have the interloop, and we use the ACT, adaptive computation time, the ACT model to control how many times this loop work. Means that how many layers we should use for the transform, no matter it is a receiver or no matter it's a transmitter. Okay, so that's due to the time limitation. I will leave this. This algorithm to you offline. You are welcome to have more detail from our published paper here. And so let's see the performance of this semantic coding based on the adaptive universal transform. So before we go to the detail, first of all, let me explain the performance evaluation matrix, the difference of matrix between the traditional communication system and the semantic coding system. Here we use the so-called BLEU scores. BLEU means that bilingual evaluation and study. It is the common criteria within the semantic signal processing area. So it means that For example, let me here give you an example. What's the meaning of BLEU scores? So here, for example, we have one sentence. The sentence weather is good today. So we have 1 gram weather is good today. If we consider 2 gram, means that the weather is. Second 2 gram is good, and the third 2 gram is good today. So means that we compare the word by words. Could it be the 1 word or could it be 2 words? So BLEU score is the standard, score standard criteria for evaluate the performance of semantic coding and semantic signal processing. So here we use the so-called the database, European Parliament database is a common database for the language sentence words. So within this database, we have there are 2 million sentences and 53 million words. So here, of course, for evaluate the performance, we use another criteria. We use another matrix. You are quite familiar with that. Is cross entropy. Means that at the receiver side, the received symbol will be compared with the labeling symbol by the cross entropy. So here on the right side is the setting of the simulation you can see that we use a transmitter, universal transform encoder on the receiver side and on the on the transmitter side, and on the receiver side we use the of course we use the universal transform encoder. So let us first look at the left picture. So so we compared, as I explained previously, we compared the BLEU, and so the black curve is the universal transform, and the red curve is the conventional transform, and the blue curve is based on turbo, and the green curve is for Reed-Solomon. So that means, and so you can see for the SNR region, we have very big performance gap between the universal transform and transform with the conventional coding system, turbo code, as well as the Reed-Solomon code. So here so this result is quite surprising for us. And that's the left picture is for the AWDN channel, and the right picture is for the relay feeding channel. So similarly, we have the very big gap between the semantic coding, between the performance semantic coding and the conventional famous turbo code and the Reed-Solomon code. So you can see from the vertical, the value almost, the difference is, 60 and even up to 80%, percentage difference here. So, of course, you are welcome to refer to the detail from our published paper here, mentioned here. And so let us move to the next one. The very interesting result we have obtained is the left picture here, left figure here, and if we compared the BLEU value between the universal transform and the turbo and the Reed-Solomon, we have realized that very big performance gap between them. But in terms of SER, symbol error rate, and of course you can see that The black curve is universal transform, and red curve is transform, blue turbo, and the green redistorment. Here again, and we in the low SNR region, the performance is UT, universal transform as well as transform. Outperform the redistorm and turbo. But for the high, SNR region, for universal transform and the transform, we have error flow here. So even in the AWGN channel. So that means, that's a very interesting phenomenon here. That means from now on, we need to find some solution, try to solve this problem, so-called error flow problem for high SNR region. So, due to the time limitation, let us move to the next slide. So here, I believe some of you are familiar with this result, where we are known from the research group of Professor Shear and Jeffrey Lee of UK. And we have the performance comparison between our algorithm UT and their algorithm transform. Basically, we had, the better performance compared with the previous transform result published by these two papers. Okay, so let us move to the third part of semantic communication. As I explained in my previous slide, you have seen this slide, and this is the general picture, general system architecture for the semantic communication with semantic coding algorithm included. And if we, look at the who transmit side, as well as the who architecture of receiver side, and on top of semantic coding, we also have other functionality blocks here, and I will give detail from now on how those algorithm works. So here, and on top of the semantic coding, we extend our work to semantic communication. And so we have designed several, for semantic communication systems, several algorithms. So here is a very general picture on how the designed semantic communication works. So from left side, you have the encoder, and then we designed the policy network, and based on policy network, we can choose the control the transmit bit rate on the transmit side. Then we move into the channel, and on the receiver side, we can have the adapt padding, and also we can have the feedback to the transmit side, right? And on the receiver side, we can put together the received word or sentence together, and to use them, as a one group. So I will give detail next slide. So here, and here is the receiver. On the receiver side, we have several decodes, and we can have the multiple decode. Also, we can have the single decode. And on the receiver side, we have the several. We have received several sentences, words right, but due to the the very channel due to the terrible channel condition, some of the words or some of the sentence might be lost. So previous simulation communication system, all the received words or sentence we just did not use them at all. But within the semantic communication, the knowledge or the information of previous received words sentence can be still used. So, and here we propose the scheme of the so-called HAIQ, hybrid AIQ, based on the incremental knowledge. Incremental knowledge means that the previous sentence have been lost, but still they have some meaning there. We can take advantage of those lost sentence and we use them again. And we send the next signal back to the transmitter and request the transmitter to resend the information, and we combine the retransmitted information bit symbol with the previously saved symbol and word together, and we then we decode them. So that's how the algorithm works. Okay. So, and that's the receiver side. Similarly, on the transmitter side, we can have the same philosophy, same idea, and we have also adapt bit rate control here, and we can have, if we have SNS, information back to the transmitter, we can use the policy network to design the encoder together with the transform, and we can control the transmit bit adaptively. Means that when the channel condition is worse, we use longer bits for one symbol or for one word. When the channel condition is better, we use a short bit. We use a few bits for symbol, and we use a few symbols for one word for one sentence. So that's the key idea. Of course, you are welcome. You are invited to see more detail from our recently published paper here. And furthermore, we can, on the receiver side, we can design based on the self-attention algorithm. We can design the, based on the transform, based on the self-attention algorithm, we can design the denoise module again. So, okay. So maybe we should back to this slide. So here is a general picture. I just give the more details on the separate function block of this general semantic communication system. So here is a general picture. If you look again at this general picture, you can understand, oh, so we have the adapt bit control algorithm. On the transmitter side, we have the adapt bit control. On the receiver side, we have the incremental knowledge-based HAIQ for the whole system. Also, we have the denoise module on the receiver side. So, okay, so let's see the performance. Finally, let's see the performance. So here is the simulation parameters for the semantic communication system. So here, I'm sorry for it's too. The words are too small. You may not see clearly the parameters for the semantic coding for the HAIQ or policy network scheme, but you can see the detail from this paper again. And of course, for the semantic code, we use the transform. And let's see the performance here. I will give a little bit detail here. So that's the numeric performance here. So of course, horizontal is the SNR, and the vertical value, is the BLEU. And we have done simulation for different coding combination scheme. And from top, let's first see the left figure. From the top to downside, performance, we have the curve. of the IK, HAIQ scheme. Then we have SC. SC means semantic coding. So that's the general semantic coding. And single means the single decoder on the receiver side. Then we have the two curve. Then further we go downside. We have the group of the conventional channel code and source coding system, source coding algorithm. We have the combination of Hoffman-Reed-Solomon and Hoffman LDPC, Hoffman Reed-Solomon with HAIQ, Hoffman LDPC with HAIQ. Of course, we have another source coding algorithm, LZW, combined with the Reed-Solomon, combined with LDPC, combined with the HAIQ, and combined with the LZW plus LDPC plus HAIQ. So here you can see, both of the IQ, HAIQ algorithm, no matter it's multiple decode, a single decode, outperform the conventional semantic coding, no matter single decoder or multiple decode. And the group of semantic coding system and the HAIQ system outperform the tremendous conventional source coding plus combined with the channel coding, no matter it's LDPC or Reed-Solomon or something like that. So that's very encouraging result here. Means that in the area of low SNI region, it's very promising to consider semantic coding. It's very promising to consider to use IK, HAIQ scheme here. So time is limited. I move to the next slide. So for this slide, we, as I explained, within my previous slide, and for the design for the proposed semantic communication, we have integrated scheme here, and SC means the semantic coding, general semantic based transform. SNR plus adaptive means that we have the adaptive denoiser module on the receiver side. And the self-adaptive means that we have the self-adaptive based on the multiple attention scheme on the receiver side. And SNR self means that on the receiver side, we have the self-attention. We can have self-attention be adaptive according to the received SNR value. So you can see that, on the right side, we let us look at this figure. SC means the general semantic coding system. Policy means that we have on the transmitter side, we design the policy, that's a policy algorithm. And the policy plus IT means that we design the policy network on the transmitter side with the debit control. And policy plus IT plus IK means that on the receiver side, on both transmitter and receiver side, we have the policy network, we have the incremental transmission, we have the IK incremental knowledge on the both transmitter and receiver side. And the last one, policy plus IK plus endows, means that we have policy network, we have the incremental transmission, debit control on the transmitter side, we have the IK on the receiver side. Also, we have the denoise algorithm working on the receiver side. So you can see from the black curve to the green curve, red curve to the pink curve to the blue curve, the performance have been gradually improved. And finally, you can see that the performance near the SNR 8 dB, the performance is almost near to the 1 point. That means the best performance there. Okay. So So finally, let me give the part of the discussion and summary. So here is a very quick, just a very general picture on what we are thinking of the semantic communication. We believe, the next 10 years, the research will not be focused on semantic coding only. We will extend from semantic coding to semantic communication. On top of that, we will have semantic network with semantic operation system there. So here, due to time limitation, just a very general picture. And we have the real physical words, but also we have the virtual information words. Between them and within each word, it is necessary or it is better to have so-called semantic operation system for both sides, both network, right? Both words. And okay, here, let me give you one detail here, one example here. And we just have done some relation in our previous work here. And you know the IP address or the routing or switching have been done with the network layer without considering semantic features, semantic functionality there. If we have semantic addressing, routing, switching, the whole picture of the network will be totally changed. Because, for example, we need not to get the contents from the very long, center. We can get the content from near the center, which near the user, based on the semantic addressing, routing, switching algorithm here. Of course, if you have any interest, you are welcome to refer to this paper as mentioned here. So finally, and let me give you a very, very quick summary on what we are thinking 6G will be. Excuse me. We have 6 points on 6G. The third point is we believe, of course, we do not have time to go to detail each items here. I just mentioned the third opinion. So we believe 6G is based on semantic communication, semantic information theory, and knowledge. So that information bit is empowered with real meaning, means that we do not just pay attention to the bits itself, we pay attention to the meaning of bits, the meaning of a symbol, the meaning of words, and the meaning of a sentence. And especially not a single bit, not a single symbol, not a single word on a single sentence. We pay attention to the relationship between bits, relation between symbol, relation between words, and relation between sentence. I believe this slide is my last slide. And of course, finally, thank you. And thank you for your attendance. And I'm open for answer any question and here. Thank you.
Thank you very much, Professor Zhang, for the very nice presentation.
So should I stop the sharing slides, right?
Actually, yeah, you can keep it. Perhaps.
Okay, great. So maybe
if you need to show us some results or something.
Yeah,
okay.
Great. Thank you. Mm-hmm.
Okay, so now we are going to move to the Q&A section. So feel free to write your question in the chat box, or if you prefer, raise your hand and make the question by yourself. Okay. We have some questions. I'm seeing the chat box. Actually, 4 questions from Dr. Honggang Zhang. So thank you, Kiang. Thank you for all the questions. The first question is, the dense layer is a bag of word model. So how to guarantee no loss of semantic information when using it after the transformer encoder?
Okay, so that's a very good question. Let's move to the, okay, it's better to go to back to, to the system model here. Yes, should be this one, right? So basically, the dense layer here is based on the, MLP, multiple layer perception. So, so the semantic information or the meaning of semantic information has been kept, already kept by transform, and after transform, the dense layer here, or we call it the MLP layer here, is is used for the functionality like something like the channel coding. So it works not exactly similar with like channel coding, but it can be, thinking can be thought of something like channel coding here. So basically, the meaning of the semantic information has been kept or has been maintained by the transform on the both sides of transmitter and receiver. So here's dense layer is working like something like the channel code or something like that. Okay, I'm not sure whether or not I answered the question from Dr. Zhang.
Yeah. Okay. Actually, with Kian, if you have if you want another clarification, feel free to write. Okay. Yeah. The question. So let's move. The second question is about the transformer encoder. So does the transformer encoder compress the message? Does it need more or less resource to transmit compared to conventional coding?
Okay, excellent question. Yes, and yes, I believe all of us are familiar with the, general, conventional, communication system. And of course, we have the source coding and we have channel coding. Before going to the IF part and antenna, right? And for the source coding, we use the, we wanted to compress the source information as much as possible. And so it's something like the compressing functionality. And here, for transform as a semantic coding, and transform as semantic encoder works something like the source coding, with some kind of compressed functionality. But here, let me strengthen that. For semantic code, for transform, the key target is not compressed information. The key target is try to dig out, try to find the relationship between different symbols and between different words, between different sentences, and keep this kind of relationship and maintain this relationship. So that's not the thing we have done with previous source coding, like the Hoffman source coding or like the LZW source coding. So that's totally different here. So of course, transform as a source coding has some kind of the function for compress the information. And also similarly, at the same time, has the actual functionality to maintain, try to find the meaning between the different words, the meaning between the different symbol, the meaning between different sentences. So that's the key difference and the key advantage of transform.
Okay. Thank you. Next question, still from Kian. Does each of the encoded semantic symbols contain different semantic entropies? Could you measure that and improve the physical layer? I mean, channel coding, HR.
Okay, great. That's a tough question. It's very difficult to answer because currently we are missing the so-called semantic information serial. And I mean, I'm not saying, I mean, the channel capacity, the channel entropy is would not work. I just want to say, and for semantic information serial, we do not have very clear model or very clear mathematic, I mean, tools to see how difference between the semantic serial and the traditional channel capacity, channel information serial. So I believe it's a very challenging work here, and it deserves, I mean, many research from now on to try to establish this kind of so-called semantic information serial. Because as far as now, within the channel serial, information serial, every bit will belong to the randomly mutual independently distribution. But for the semantic information, the story is totally different. The bits, the symbol, the word and sentence, they are connected. They have the internal mutual relationship. So how to model this kind of relationship mathematically is still is an open problem here. So that's why until now, for semantic coding and semantic information, semantic communication, we use the cross entry as a matrix, as a criteria to evaluate the communication coding performance or communication semantic communication system performance. But I believe it is definitely necessary to have different, I mean, criteria or metrics solely based on the semantic information serial. That's the work, that's an open problem.
Okay, thank you. So
okay, thank you, you're welcome.
Yeah, one more question, still from Kiang. I think is his last question. The question is, since different deep learning architecture are designed for various data structures, text, image, graph, so would you think there is a need a generic semantic communication framework, and how it can be standardized?
Oh, great. This question is very, I mean, technical. I like this question very much. And because, I mean, from this question, we know that, I mean, deep learning architecture, we have transform, we have GNN graph neural network, we have the CNN convolutional neural network. So of course, for communication system, we need to have unified, I mean, framework. And since we transmit the text, this image or graph, even the video, so my answer to this question is that personally, I believe transform is the best choice compared with the CNN, compared with the GN. The reason is that transform can be used not only to the area of the sentence of text. Just in recent 2 years, transform has been applied to the image, to the picture, to the video, and it is so-called time spatial 2D transform. So it's a very hot topic, even within the research community of artificial intelligence and machine learning. They have done very excellent work recently on how to use the transform to improve the performance of the recognizing on the image processing, on the graph processing, video processing. So that's why I believe transform is not suitable not only to sentence, to words, to text only, but also suitable to image, graph, video as well. So that's the feature that CNN, GN both of them do not have. So that's why I believe transform, I tend to believe transform will be the very promising solution from now on, consider the unified framework for communication, semantic communication. So that's all. That's my answer.
Thank you very much. One question from let me see, from Badreddine Noon. So the question is, how does the memory computational complexity of transformer impact user equipments in terms of cost, complexity, hardware complexity? And are these transformers pre-trained? Could we offload the complexity to the central unit and base station, for example, and use knowledge graphs to learn how to represent the relationships and semantics and the corresponding temporal variations?
Okay, that's a very good question. From engineer side, of course, we are all of us are the telecommunication engineers. And from engineer side, from now on, it should be clear answers. I mean, we should clear answer these questions. And yes, we have some very preliminary, I mean, analysis on the complexity of the whole semantic communication, on the whole, the complexity of the transform, and yes. But for the detail, please, I mean, I show this slide, and we just published the paper, uploaded to our archive. Please read this paper with details. And within this paper, we have done some preliminary comparison between different algorithm transform or the neural network and something. Of course, currently, I mean, due to the, I mean, the complexity of the neural networks and something, I mean, I do not want to say currently we can use in practical scenario immediately the chip of transform or the chip of something. Neural network or something like that. But I'm quite positive at the direction future. I mean, at least for the 6G, we have at least 8 or 10 years. I believe the development of chip will be very quick from now on if we have very, important application scenario waiting for us or for the industry. I believe that the chipset of the transform would not be a big problem there. I mean, I'm positive at this point.
Okay. One question from anonymous attendee. I think he or she didn't reveal the name, but the question is, what's the difference of cross entropy and BLEU? I mean, bilingual evaluation on the study.
Okay, great. I'm sorry, maybe I did not give very clear, explanation on the definition of BLEU and cross entropy. Here, the BLEU means that, that's the difference between the word. That's the common standard used to language processing. So we have, 1 gram, 2 gram, and 3 gram, even 4 gram. That's different between the transmitted and the received word text. How to calculate the difference between the different text. The text could be a word or the sentence, word by word, 1 word, 2 words. That's the BLEU. So cross entropy is, as defined here as an equation. That means that on the receiver side, we have decoded information right there. And of course, we have during the training, we have the labeling, we have the target information. So that's the difference between the actually received information and the labeling as a target information. That's the difference between them, and and that means cause the loss. So we calculate how to calculate the loss between the really received information and the target labeling information. That's a difference. So we use the cross entropy to calculate this, to model this difference. So here's for example, here LCEC cross entropy. Of course, S head is the sent sentence, source sentence, and the received sentence information. Alpha, beta, gamma are the hyperparameters for the transfer from the neural networks. So here the WL means the L's word, and P and Q means the distribution probability of that word. So that is the very common equation for the cross entropy. I'm not sure whether or not I answered the question.
Okay.
Yeah,
it's okay. The last question is from Dr. Shiguan He. The question is regarding the adaptivity with variant CSI or CSI feedback. It's mentioned the adaptation can be done at the semantic coding. How about joint adaptation of semantic coding and channel coding, even taken in consideration for modulation?
Okay, great. Frankly, that's the next research for our group. So now we have done the semantic code, right? And let me move to the simulation result here. Okay, here, and of course you can see that we have different performance. Of course, the semantic code coding system outperformed the conventional combination of Hoffman, Reed-Solomon, LDBC code. But we believe, it is still meaningful to take advantage the LDBC code or Reed-Solomon code combined with the semantic code, because we have done so many excellent research, so many work on improve the channel code. So why not combine the advancement of semantic code with the advantage of the traditional channel code? So that may be a win-win approach. Of course, this work is still on. It's our next step work. We hopefully will give some results as soon as possible to try to combine the semantic code with the conventional channel coding to see whether or not we have the double time or the win-win approach performance here. So it's the work to be done from now on.
Okay, thank you. I am not sure. I think we don't have more questions from the attendees. Yeah, we had around 20 minutes, 25 minutes of discussions. I think it's enough. And maybe I'm going to proceed with the end of this Telecom seminar. And I would like to thank you once again, Professor Zhang, for delivering this talk and for sharing your recent results and research with us. And also would like to thank our attendees to join us in this Telecom seminar. And actually, every 2 weeks we are organizing a Telecom seminar. So please keep an eye on this schedule, and hope to see you. To see everyone in 2 weeks. Thank you. Professor Zhang, if you want to say your final words, please.
Okay.
Feel free.
Okay, thank you. And of course, first of all, I'm really sorry for the disturbance during the presentation. Some of you might have lost the sentence, and due to the quality of the internet, the voice access, voice language access here.
That's good. Don't worry. And
Okay.
actually, we recorded we are going to record all the seminars. So for those who want to see again the seminar, it will be made available online very soon in our at TII website.
Okay, great. And
Thank you.
of course, thank you, Daniele, and my personal thanks to you, and appreciate your organizing this seminar. And also, I will, as a common practice within the research community of AI and machine learning, it is better to open all of the source code and presentation material there. So my group, I will open my presentation material slides in the near future, and we will upload the code, the source code, through the GitHub database. So of course, any research you are interested in this topic, you are very welcome to refer to those codes and those source code and program, and we hope we will work together in the near future, try to pushing forward the research of semantic code, semantic communication, and the semantic network. I personally believe that's really, really big thing for the next 5 to 10 years. Okay.
Thank you. This is a very good initiative. Yes, sure, we are very a good material, and many people you download, and will be very useful, especially for those who are starting working in this very emerging research topic. Thank you once again. Thank you, everyone, and see you in 2 weeks.
Have a good night, right? Not night. Okay.
Yeah, here is almost night.
Okay. See you.
Bye-bye.
See you face to you. Bye-bye. Thank you.
Bye.